Okay, in this segment, what I want to do is say a few more things about the early effect. So, last time we modeled the early effect. We talked about sort of where the early effect was coming from. The fact that as we increase the voltage on the collector of a transistor, the collector to base depletion region gets a little wider, and that makes the base a little narrower, which increases the concentration gradient of the electrons flowing through the base, and that slightly increases the current, because the current is proportional to that concentration gradient, which is inversely proportional to the slightly shorter width. And so we developed a empirical model, effectively, which involved having our idealized transistor, the base and the emitter. And we imagined where we want to take into account the early effect, we put a resistor whose value was RO in parallel with our ideal transistor, so that the current here, IC, was kind of an ICO plus a VCE over RO, where this is VC. And so we have something like IC is equal to ICO times 1 plus, it was ICO plus VCE over RO. And RO we could write as ICO times VCE over VA, and we could factor out the 1 plus, or the ICO, and we'll have this 1 plus VCE over VA, where ICO is sort of the 0th order collector current, which is just given by our model IS e to the VBE over UT. Okay, and we had this idea that if we thought about a collector characteristic, we had this sort of component which was ICO, we had this component which was sort of an Ohm's law, and then when we add those two up, because they're connected in parallel, we would get something that looked like the collector characteristic that we measure. Okay, that's just all review. I want to bring out a couple of things. So if I take this collector characteristic, IC as a function of VCE, and we have our collector characteristic maybe like this. I've exaggerated the slope here. The slope of this line is 1 over RO, the output resistance of the transistor. If I take this, a straight line fit to this sloped collector current characteristic, and extrapolate it back, there's an intercept, the y-axis intercept, and there's the x-axis intercept. Okay? And this y-axis intercept is this thing over here, which we called ICO. Okay, that's the 0th order collector current. So if we imagined having a transistor that's ideal, operating with this VBE, it would have a collector characteristic picked out from the family, and that would be the ICO value. When we add in that extra current due to the early effect, that raises the slope of this characteristic up by some amount. And if we imagine this model here, where we plug in VCE equals 0, we just are left with ICO. Okay, so the y-axis intercept here is ICO. If we ask, where is the current go to 0 on this model over here? Okay, well, that would be for VCE is equal to minus VA. So on this graph here, the x-axis intercept is minus VA. So the early voltage is a positive number, okay? It's a number like 25 volts or something like that, or 50 volts. But where it lives on this collector characteristic graph is the negative of the x-axis intercept. Okay, so the x-axis intercept is minus VA. So this is the negative of the early voltage. And last time we typically assume that VA is more or less constant, and that means that if we have a different set of a different characteristic for a lower value of VBE, it would intercept the x-axis at that same value. All of these curves, for all the curves in the family, would all intercept the x-axis at that common point. That would be a constant, often assumed constant. Okay. In practice, it's not quite constant, but it doesn't vary by orders of magnitude. It might change by several percents or tens of percents as the collector current varies over the 6-decade range that it has. So it's a good assumption for sort of zeroth order modeling to take that as a constant. Okay, so that's what we will do for the most part. So that's one piece of what I wanted to talk about. I also wanted to talk about an alternative model, an alternative empirical model for the early effect, okay, to this one. Okay, so I'm going to call an exponential early effect model. Okay, so our early effect model was IC equals, let's say, IS e to the VBE over UT times this empirical factor, which was 1 plus VCE over the early voltage VA. Okay, so this is a conventional linear model. What I want to consider is an alternative model, which is IC equals IS e to the VBE over UT times an exponential factor, which is e to the VCE over VA. Okay. So, why is this potentially a good idea? Well, for small x, we know from calculus that e to the x is approximately 1 plus x squared over 2 factorial plus dot dot dot. All right, we can do a Taylor series expansion of e to the x. Actually, it's a Maclaurin series expansion, or it's equal to this. And then for sufficiently small x, it's approximately equal to 1 plus x. Okay, that's the way we conventionally run the approximation. We say, well, we can see we have an e to the x. We can linearize it for small changes in x about 0 as 1 plus x. And we approximate the exponential characteristic for small changes by this polynomial, okay, first order polynomial function. But there's no reason we can't go the other way. Right, so we can also say for small x, 1 plus x is approximately equal to e to the x. Why not? That may not occur to you as the first thing you might want to try for something, but we have this model, the conventional linear model, and what we have here is a factor that's of the form 1 plus x multiplying our exponential form out front. Well, here what we're saying is that if this VCE over VA is sufficiently small, then e to the VCE over VA should be a good approximation to it. And VA is a number that's typically for a bipolar transistor maybe on the order of, like I said, 25 volts. And if our VCE is in our power supply range, which might be, let's say, 0 to 5, or maybe 0 to 3.3 or something like that, or 0 to 1, we're in a range where we are actually, VCE over VA is, less than a fifth or less than, it's like a tenth or something like that. So it's in a range where it's actually fairly small. And so this approximation should be a good one. So why might we want to consider having this exponential form rather than this polynomial form? Well, it has to do with the kind of equations we're dealing with, right? So when we write down Kirchhoff's current law equations involving things like bipolar transistor emitter currents or collector currents, we have these exponentials running around. And when we mix them with a polynomial factor, we usually wind up with things that involve the products of polynomials times exponentials, and those things don't really lead to tractable equations. But if we take our exponential model, right, because the product of two exponential factors we can write as IC IS e to the VBE over UT plus VCE over VA. Well, now we just have a single exponential factor here. And often what we'll be able to do is take the log of both sides of an equation, and then we get a simple linear function that involves VBE and VCE. And we'll see some examples of this. So by using this alternative formulation, when we're doing a large signal analysis, when we have these exponential models for the IV relationships, this can sometimes lead to very simple results and allow us to account for the early effect. And we'll see some examples of this before too long. I think we're going to go through an example where we assume that the early effect is negligible, and we'll do a large signal analysis, and we'll find a nice simple result, and then we're going to go back in and say, well, what if there was an early effect? What would the analysis look like in that case? And we'll see how it changes the result. Okay. And we'll be using this type of model because it's going to simplify things for us quite nicely. The third reason we might want to consider a model like this is, for instance, shown here. If we go back to this slide, now these are the reverse emitter or inverse active collector characteristics that I showed for this one transistor that I had measured data from in a slide deck that I did a couple of sessions ago. And you can see that we have this nice sort of linear looking curve here for fairly small VCE. But when we get up to about 3 volts, we see that this starts taking off and is concave up. We're starting to go up that breakdown curve. And it turns out that this factor of e to the VCE over VA, as we are calling it in the slides, is actually a better way of capturing what's going on here qualitatively with these expansive nonlinear characteristics than the factor 1 plus e to the VCE over VA. And so we can go a little further up the breakdown curve here, possibly, and still maintain a nice qualitative empirical model of what's going on. in a way that's better than the linear model that that Early originally applied to this device. Okay, so that might be a third reason. So it's a good approximation for a sufficiently small VCE to VA ratio. So there's no reason we can't run the usual Maclaurin series expansion of e to the x in reverse and take a 1 plus x and approximate it as e to the x. And that leads to a form that's often a better match for the types of functions that we have running around in our equations when we're doing large signal analysis with an exponential model, the ISE to the VBE. So it's more compatible than the polynomial way of modeling it. And third reason, again, it is that it's probably even a slightly better model than the linear factor for slightly larger values of the ratio VCE to VA, as we can see with these sort of typically expansive nonlinear collector characteristics. If we were to take the forward characteristics out a little further, we would start to see them do the same thing. And so it may even in fact be a better empirical model than the usual conventional linear one. Well, that's all I have for this particular segment, so this is a little shorter. Next time we'll look at our first two transistor bipolar circuit and think it through and analyze it. See you next time.